Hello. The initial quote today is from Professor Comer. The use of compositions of beach sediments to identify their sources is often one component in the development of a budget of littoral sediments. Another quote from Professor Comer is the sediments budget is simply an application of the principle of mass conservation to the littoral sediments. The time rate of sand change within the system depends upon the rate at which sand is brought into the system versus the rate at which it leaves the system. The budget of littoral sediments considers the balance between inputs and outputs. The inputs can be from a longshore transport into an area, the river transport, the sea cliff erosion, the onshore transport by waves, the biogenous deposition, the hydrogenous deposition, the wind transport onto beach, and the beach nourishment. The outputs can be longshore transport out of an area, the wind transport away from the beach, the offshore transport, the deposition in submarine canyons, solution and abrasion, and mining and dredging. Those in red are human-induced inputs and outputs. The balance between inputs and outputs results in beach accretion if this balance is positive, or beach erosion if this balance is negative. Now, starting to illustrate that, the concept of input versus outputs are also known as sources versus sinks. And in this image, we have some of them. Take a closer look. It's not an easy task to quantify the sediments budget of a particular segment of the coast, but this is important to coastal engineering solutions and to the geomorphological understanding of the coast. The idea of point sources or point sinks came from the understanding that these are sources or sinks that add or subtract sand across a limited part of a control volume boundary. A tidal inlet often functions as a point sink. Point sources or sinks are generally measured in units of volume per year. Thinking about line sources or line sinks, these are sources or sinks that add or subtract sand across an extended segment of a control volume boundary. Wind transport landward from the beaches of a low barrier island is a line sink for the ocean beach. Line sources or sinks are generally measured in units of volume per year per unit of shoreline. This table presents the classification of elements in the littoral zone sediment budget is from the Shore Protection Manual and classifies as point sources the offshore shoal or island, rivers and streams, the beach replenishment, and longshore transport. For point sink, there are submarine canyons, inlets, mining and extractive dredging, and longshore transport also. From line sources, they classify the sand transport from the offshore, the coastal erosion, including erosion of dunes and cliffs, and beach erosion, or CaCO3 production. From line sinks, they classify sand transport to the offshore, the overwash, coastal land and dune storage, and beach storage or CaCO3 losses. Now let's talk about some of the sources. From rivers, it's estimated that rivers in the world bring about 10 to 20 billion metric tons of sediment to the coast each year. Only a small percentage of this sediment is in the sand size range that is common on beaches. The large rivers, which account for most of the volume of sediment carried, a relatively little sand. Most sediments carried to the coast by rivers are deposited in comparatively small areas, often in estuaries where the sediment remains trapped. The small fraction of sand in the total material brought to the coast suggests that rivers are no immediate sediment sources on beaches for most world's coastline. Erosion of shores and cliffs. Erosion of the nearshore bottom, the beach, and the seaward edge of dunes, cliffs, and the mainland results in a sand loss. In some areas, erosion from cliffs of one area is the principal source of sand for downdrift beaches. Cliff erosion accounts for only about 5% of sediment supplied to coasts and is thus significantly less important than river supply. Coastal cliffs are a prominent feature of both hard rock and soft rock coasts. The retreat of soft rock cliffs may release sediment for in situ beach development over a shore platform or transport along shore onto beach sinks. In contrast, mud released by cliff erosion are generally deposited over calmer coastal and estuarine depositional environments such as mud flats and salt marshes. Shore erosion is a significant source where older coastal deposits are being eroded since these usually contain a large fraction of sand. Another source is the transport from offshore slope. Contributions from the continental shelf to the littoral zone are probably negligible in many areas. Most shoreward moving sediment appears to originate in areas fairly close to the shore. Significant onshore and offshore transport takes place within the littoral zone due to seasonal and storm-induced profile changes and to erosion of the nearshore bottom and beaches. Transport from the offshore has been treated as a line source. Another source is the wind-blown sediment sources. To make a net contribution to the coast in the time frame considered, wind-blown sand must come from a land source whose sand is not derived by intermediate steps from the same littoral zone. Wind-blown sand can be an important source if the control volume being considered is a beach on the lagoon side of a barrier island. Such shores may receive large amounts of it. One more source is the carbonate production. In tropical areas, many beaches consist of calcium carbonate sands. In temperate zones, calcium carbonate may be a significant part of the littoral material. These are generally fragments of shell material whose rate of production appears to increase with high temperature and with excessive evaporation. Other significant source is beach replenishment or beach nourishment. Beach defense projects often require placing sand on beaches. The quantity of sand placed on the beach in such beach fill operations may be a major element on the local sediment budget. Later on, we are going to talk more about this kind of operations. Now we are going to talk about some of the things for the coastal environment, starting with inlets and lagoons. Barriers are often interrupted locally by inlets, which may be kept open by tidal flow. A part of sediment in a longshore transport by wave action is moved into these inlets by a tidal flow. Once inside the inlet, the sediment may deposit where it cannot be moved seaward by the ebb flow. Inlet traps significant quantities of sand. Another thing is the overwash. On low barrier islands or barrier beaches, sand may be removed from the beach and dune area by overwashing during storms. Such rates may average up to 0.5 cubic meters per year per meter. Overwash does not occur on all barrier islands, but if it does, it may function as a source for the beach on the lagoon side. Other thing is the backshore and dune storage. Sand can be temporarily withdrawn from transport in the littoral zone as backshore deposits and dune areas along the shore. These sands may remain in storage for intervals ranging from months to years, depending on the frequency of major storms. Backshore deposition occurs in hours or days by the action of waves after storms. Dune deposits require longer to form because wind transport usually moves material at a lesser rate. sinks are related to offshore slopes. The offshore area is potentially an important sink for littoral material. Transport to the offshore is favored by a. Storm waves which stir up sand, particularly when onshore winds create a seaward flow. B. Turbulent mixing along the sediment concentration gradient which exists between the sediment water mixture of the surf zone and the clear water offshore. C. The slight offshore component of gravity, which acts on both the individual sediment particles and on the sediment water mixture. Another type of sink are the submarine canyons. In some areas, an important sink for littoral sediments is submarine canyons. The relative importance of submarine canyons in sediment budgets is largely unknown. Once inside the canyons, the sediment travels down the floors of the heads of the canyons and is permanently lost from the littoral zone. Another important sink is deflation. The loose sand that forms beaches is available to be transported by wind. Such erosion over the total beach surface can amount to significant quantities. Unstabilized dunes may form and migrate landward, resulting in important net loss to the littoral zone. The largest wind-transported losses are usually associated with accreting beaches that provide a broad area for loose sand over a period of years. Another important sink for the coastal environment are anthropogenic. We are talking about the mining and dredging operations. From ancient times, sand and gravel have been mined along coasts. In some countries, mining has undesirable effects on coastal settlements in the vicinity. Mining must be conducted far enough offshore so the mined pit will not act as a sink for littoral material, or refract waves adversely, or reduce the wave damping by bottom friction. The boundaries for the sediment budget are determined by the area under study and the time scale of interest. It's quite important to consider shore parallel boundaries and shore perpendicular boundaries. Shore parallel boundaries in an open coast can be defined arbitrarily, like in this example. In this case, it must consider the dominant wave attack firstly. The obliquity angle of approximation of the waves and their significant heights along the year will define the directions and intensity of the longshore transport. Considering the defined boundary limits for the sediment transport, the longshore currents must be defined as a source from where it's coming in and must be defined as a sink to where it's going out. The cross-shore sediment transport evaluation can initiate defining the rate of beach erosion in our boundary limits. Those eroded materials can be transported both by the longshore currents and to an offshore sink. All of these rates can be quite precisely modeled and calculated. Time for another quote from Professor Davison Arnold. The modification of the coast takes place through the erosion, transport, and deposition of material that is either eroded by waves, transported by rivers or currents, and brought to a specific segment of the coast. Now let's talk about sediment transport processes. Fine sediments, silts, and clays do not occur in appreciable amounts in the inner nearshore and surf zones on energetic coasts. They tend to be placed in suspension and diffuse uniformity through the water column, maintained by turbulence. Sand and gravel fractions are cohesionless and readily set in motion by waves. They are exchanged readily between the inner and outer shore face and the beach and may be transported alongshore in significant quantities. Thus, they are characteristic of most beaches and surf zones. Cobbles and boulders are larger particles and are also cohesionless, but their size also requires special treatment and transport requires very large waves or possibly the presence of ice. From now on, we are going mostly to talk about sand and gravel fractions. In this context of sediment transport processes, there are some complexities. The effects of breaking waves and turbulence within the surf zone add a level of complexity to coastal processes not encountered in hydraulics. With their oscillatory velocities, the waves, the nearshore circulation, and winds drive beach materials cross-shore and alongshore in a complicated way. This coastal sediment transport will be referred to as littoral transport from now on. The motion of particles is caused by forces acting on them. Look at this image. The Fd is the drag force, the Fl is the lift force, and Ws is the weight of these particles. Those forces interact to put the particle in motion. This is an overview of the littoral transport, the bigger picture of the littoral or sediment transport. As we already know, waves and currents are the main driving forces. And regarding the waves, it is important to understand some concepts of the generation and propagation of wind waves and swell waves and maybe infragravity waves. Regarding the currents, some of them are generated by breaking waves. That's the example of longshore currents. Tidal oscillation generates some currents, and we name them as tidal currents. Winds mostly generate ocean currents over the sea surface. All of them interact, including when some river flows join the coast. Obviously, important for sediment transport are the sediment properties like density, size, and their distributions. Those interactions lead to the estimation of sediment transport quantities that, if it is significant, lead to morphological change by the end of the day. The morphological change itself will influence the sediment distribution and behavior of the driving forces at the coast, which will also be different from the previous state. If we look closer to the water column, sediment transport presents some interesting characteristics. From the bed to the surface, there are different patterns of transport. Some sediments don't move, they compose the bed. Some of them jump, roll, and slide along the bed, which composes the bed load transport. Finer materials compose the suspended load transport because waves stir up the sediment and longshore currents transport them along the coast. The total sediment transport is composed by the longshore sediment transport and the cross-shore sediment transport. The longshore transport is important in the long term, years or decades, and also in the short term, maybe seasonal patterns of the longshore transport are important to coastal processes. Important quantities involved in longshore transport are related to wave height, wave direction, water level, sediment properties. The cross-shore transport is mostly important in the short term, like seasonal storm cyclones and single events. Important quantities involved in cross-shore transport are wave height, water level, sediment properties. The longshore transport can occur in two alongshore directions depending on waves angle approaching the coast. By convention, an observer looking out to the sea will denote longshore transport as positive when the sediment is transported to observer's right and negative when it's for the left. Typically, the longshore transport at a site will consist of positive drift for one or more seasons and negative drift for the remainder of the year. Some more important concepts for the longshore transport are the net drift, that is the sum of the positive and negative components of longshore transport, and the gross drift, that is the sum of drift magnitudes, not considering direction. In this example, we can see clearly waves and currents that are approaching from north to south. But in this specific location, the net drift along the years is from south to north and forms that kind of pattern of coastal deposition that we can see in this image. The Cirque in 1984 developed the most used equation for longshore sediment transport. This equation is the Q that considers an empirical coefficient named K, it is 0.39, rho, that is the water density, rho s, that is the sand density, g, that's the gravity, a, that is 0.4 on porosity index, hsb, that is the significant wave height at breaking point, and theta, that is the wave angle at breaking. This equation is based on the principle that the longshore transport rate is proportional to longshore wave power per unit length of beach. The cross-shore sediment transport is a result of water motions due to waves and undertow, and are responsible for major changes in seasonal beach profile, including bar formation. This is an example of a beach profile, and there is the black line with the summer profile, and the dashed line with the winter profile when beach was eroded and bars were formed in the surf zone. This is a schematic representation of shape function effects on profile morphology. Subtidal nearshore sandbars are common features of beach profile morphology, and their dynamics tend to dominate profile variability. Bars affect nearshore waves and circulation, and consequently sediment transport and morphological changes. The bar migrates, and their migration magnitude and direction are controlled by the incoming wave energy level. In storm conditions, the offshore transport dominates. In calm conditions, onshore sediment transport acts over the bar during fair wave conditions, and this makes the seasonal beach profiles that we already know. Those already described circulation transport patterns, like the longshore and cross-shore sediment transport, in the nearshore zone can be part of the system named Nearshore Circulation Cell. This is associated with wave action in and near the breaker zone and consists of shoreward mass transport of water due to wave motion carries water through the breaker zone in the direction of wave propagation. Movement of this water parallel to the coast as longshore currents. Seaward return flows, such as flow along concentrated lanes known as rip currents. Longshore movements of the expanding head of the rip current. Those elements will be best described in a couple of other classes like waves in shallow water and beach morphodynamics. Let's practice in this fourth exercise You must search for some images, maybe photos or satellite images of Asian coast. You are supposed to find at least one image for each one of these elements studied today. Point sources, point sinks, line sources, and line sinks. Write a simple report, pasting those images, identifying their locations, type of coastal feature, and maybe any other information you judge necessary. Good luck! The simple report must be sent to my email address. Enough for today. See you soon. Take care and be safe.